Now I'm going to start recording this. Okay. All right. So again, welcome back, guys. I hope you're all doing good. And so just to recap what we have been doing so far in the class. In the last class, we looked at, or in the last few classes, we looked at the K-maps, and using K-map as a technique, and looked at some examples, some applications of K-maps, right? So basically, we looked at circuits like code converters, circuits like display decoders that we can actually use to interface your digital world to the external world, right? So we looked at one of the examples in the last class, the 7-segment display decoder that can be used to display information in the format that that a user is more familiar with. Okay, and we also looked at the parity generator. Again, these are all simple examples on how we can actually use K-maps to build some useful functional circuits. Okay, now in today's class, we're going to shift gears a little bit, and we're going to cover some important concept on modular design. Okay, now, and again, this concept of modular design is not just applicable to this class. Okay, as engineers, you should always think modular in terms of modular design, coming up with modular design, okay, to build complex systems. All right, so let's get started on that. So towards that, let's actually start building arithmetic circuits that can actually perform arithmetic operations like addition, subtraction, and so on. Okay, at this time, since we are dealing with binary numbers, we'll consider binary adders and binary subtractors to start with. Okay, now let's say I start with a very simple problem. Let's say I want to design a circuit that can add two binary numbers, two binary bits, for example. Okay, so how do I design a circuit? First of all, I'm trying to design this. Again, the design approach is again common, right? So first of all, when I'm trying to design something, I need to come up with the level 0 design, where I would specify what I'm trying to design in terms of what are the inputs to the system, what are the outputs to the system, and what the system should do really with the inputs, how the inputs and outputs are related, right? So let me start with the level 0 design for that. Again, this is a, adding two binary bits. It's very, again, do we need a design for that? Do we need actually a circuit for that? Let's see. So for this, so what am I trying to do? I'm trying to design a circuit that can add two binary bits together. Okay. So in terms of the inputs and the outputs, how many inputs should the system have? Let's say this is the circuit I'm trying to design. How many inputs should that system have, and how many outputs should that system have? If I want to design a circuit, two inputs, okay, I need, because let's say I'm trying to design, it's a single bit adder, right? So it needs two inputs. Do that here. Let's say I'm trying to design something that adds A0 and B0. These are two binary bits. A0 can take 0 and 1 values. B0 can take 0 and 1 values. So two binary bits. Okay. And how many outputs should I have? By the way, I have one output. Now, when I'm adding two binary bits, what are the different possibilities? I can add 0 to 1, and add 1 to 0, and I can add 1 to 1, right? When I add 1 to 1, how many outputs do I have? I have two outputs, right? I have the sum and I have the carry out as well, right? Because 1 plus 1, the sum is 0, the carry out is 1. I have an end carry. So I need to have two outputs. I'll call this to be the sum, S0, and the carry out to be C0 or C out. So I have two outputs here. So that's A0, that's one of the input. B0, that's one of the other input to that single bit adder. Okay. Okay. Bit better. Yeah. Still blurry. Okay. So C0, S0. Okay. Maybe I should just write a little bit. Okay. Actually, use a black pen here. That will be better. So A0, B0, two inputs. A0 can take 0 or 1. B0 can take 0 or 1 values. And then I have as the output, I would have C0, the carry out, and S0, the sum. Right? Okay. Now, once I have this information, it's a pretty simple circuit to design. Right? Let's put that information down in the form of a truth table. Okay? And let's actually do that. You don't even, because these are just two inputs, you won't even need a K-map for that. I can directly get from the truth table. So let's do that. So I have my outputs, my inputs are A0, B0, and my outputs are C0 and S0. Right? And again, you know what we need to do. We look at all possible combinations between A0 and B0. So these are all the different combinations. Now when A0 and B0 are 0, 0, basically I'm adding 0 to 0. My sum is 0 and my carry out is 0. My sum is 0, my carry out is 0. When I'm adding 0 to 1, my sum is 1, 0 plus 1 is 1. And then my carry out, I don't have a carry out, so the carry out is still 0. 1, 0, same thing. My sum is 0, well, my sum is 1, carry out is still 0. 1, 1, my sum is 0, because my sum is basically 1, 0, where my 1 is the carry out, right? Because 1 plus 1 is 2, right? And 2 is basically 1, 0 entirely. Now from this truth table, can we get what my S0 should be? What should be my S0 from this truth table? You can see that, S0 is 1 when A0 is 0, B0 is 1, or when my A0 is 1, B0 is 0. So that basically corresponds to the XOR operation, right? That's an XOR between A0 and B0. My S0 is simply A0 XOR B0. What about my C0? What should be the logical representation for C0? Maybe, right? My C0 is a 1 only when A0 and B0 are both 1s. So my C0 is A0 and B0. So now I've designed a simple circuit that can actually add two binary bits together. Of course, it's not a very useful circuit because I can do that in my head, right? But let's note it down anyway. We call this adder that adds two binary bits together. We call this the half adder, and you'll see why we call this a half adder. Just hold on to that for now, half adder. Okay, just hold on to that thought, and then we'll come back to that and see why we call that half. Where does the half come from in the first one? All right, so that's the half adder. Now, of course, it's not a very useful circuit, really. I mean, 2 bits. If I can do this in my head, why would I need a circuit that would for this? Right? Now I want to design, let's say, if I want to design a 2-bit adder, okay, a 2-bit adder. That means now I'm talking about A1, A0, because now I'm talking about 2 binary bits for each number, right? And B1, B0. That's this is my first binary 2-bit number, first 2-bit binary number, 2-bit number. This is my second binary 2-bit number. I'm trying to add these two together. Okay. And let's say I want to design a circuit that can do this. Right? How do we do this? Again, I'll put down that information in the form of a level 0 diagram. Okay. And how many inputs do I have here? For this particular circuit, how many inputs do I have? A circuit that would add 2-bit binary numbers together. I have 4 inputs. Perfect. Yep, perfect. So those inputs are A1, A0, B1, B0. Right? How many outputs would I have for this particular circuit? Sorry? Outputs. I'm adding these 2 binary bits together. Okay? Sorry? 4. Okay, let's 3, right? Why? Because let's take an example. Whenever you're in doubt, let's put actual numbers together. Okay, let's say I want to add 1, 1 to 1, 1. Those are the largest possible numbers in 2 bits. If I add these two together, how many outputs would I have? 1 plus 1 is 0. 1. 1 plus 1 plus 1 is 1 with an output carry of 1. So I need to have at least 3 bits as output. Right? I need to have at least 3 bits as output. 2 for sum, this represents the sum, and that's the end carry or the carry out or the end carry. Okay. So let me call that carry out, or I can also call that the end carry because that happens at the very end. Okay, so I have 3 bits. All right, so I have S1. Call that S1, S0. So let me call that S1, S0. Let me call that C out, that's the end carry, and then S1. Will I be able to design this using K-maps? I should be able to, right? Because I have 4, basically I have to take a 4 input K-map, 16 cell K-map. I have 3 outputs. We know how to do this. I've done similar examples before when I'm trying to design a circuit that have multiple inputs based off of the same multiple outputs based off of the same inputs. I would basically take each output to be independent and then find the function in terms of the inputs for each of these functions independently, and then basically I put together the circuit, and that's that. So I can easily able to do that using the K-map approach. Okay, but again, you know, if you think about a 2-bit adder, what is the maximum 2-bit number you can have? 3, right? So basically you're looking at an adder that can add at max 3 plus 3, which is 6. Again, that's something that you can do in your head. You don't really need a circuit for you to do that. So I'm not going to go through this entire implementation now. That doesn't really make sense. Now, if I want to get a little bit more complicated, if I want to design a circuit that can add 3 bits together, or if I want to design a circuit that can add 3 binary bits together. Let me put it the right way. I want to design a circuit that can add 2 binary numbers that are 3 bits long. In this case, by extrapolation, basically I have 3 or 6 inputs going to my system. In this case, I have A2, A1, 0, B2, B1, B0. I have 4 inputs, 4 outputs, C out, that's the end carry, and 3 sums. S3, S2, S1. Okay, let me do one thing. Any better now? Okay, thank you. All right, the 3 bits, 3 binary bits. I get what? How many outputs? How many inputs? I have 6 inputs, 2 power 6 number of cells, right? And 4 outputs. It's already getting complicated with the K-map. You see this? I have 64 different. If I want to design a 3-bit adder, an adder circuit that can perform addition between two binary numbers that are 3 bits long, I need to be, if I want to design that at the K-map level or at the gate level, I'm looking at 2 power 6 cell K-map and trying to implement that. In practice, yes, you can do that, right? But not a very efficient way to do that. And of course, even with 3 bits, the maximum number that you can represent, a binary number that you can represent in 3 bits is what? Is 7. Right? So at most, you're looking at the maximum sum of 7 plus 7. Again, something that you can still do easily in your head. Don't really need a circuit that can do that. All right. So obviously, this is definitely not good. So now, the idea is we cannot rely on K-maps only to design complex circuits, complex systems, just using at the gate level. Relying on K-maps is similar to saying I want to build everything at the gate level. It's almost like saying I want to build a big, let's say, a table using single atoms of data. That's not the right approach. Okay. All right. So now let's look at the modular approach. The idea is we will, instead of doing this approach, we'll try to build simple modules using the K-map. We'll still use the K-map, but we'll build simple modules. We'll build simple modules, and then we'll put together those modules to build a more complex circuit. Now, if I want to build an n-bit adder, let's generalize that to n-bit adder. My n can be a large number. N can be as long and as large as 32 bits. If I want to build a 32-bit adder, how do we do this? Okay. So, in order to think about that, let's actually examine the addition operation itself. Let's say I'm trying to add 2 n-bit numbers together. In general, n-bit numbers. Those 2 n-bit numbers are an minus 1, an minus 2, so on. Let's say this is ai, some intermediate bit, and a3, a2, a1, a0. And then I'm trying to add that to bn minus 1, bn minus 2, then bi is my intermediate bit position, then we have b3, b2, b1, b2. These are 2 n-bit numbers, so let's, I don't have an en. So 0 to n minus 1, that's n, total number of bits. I'm trying to add these 2 numbers together. Okay. What do I have? Again, how did you do the addition operation? Right? You start with the rightmost bit, and then you go towards the left. So you add these two bits together first. Okay. You get the sum. Let's say the sum is S0. You may get a carry out, right? Because if A0 and B0 are both ones, I may have a carry out. What is happening to the carry out? Basically, that we are using the carry out as a carry in for the next bit position. Right? This is C0, adding C0 to A1 and B1. Right? So for the subsequent bit, we're adding these two bits together along with the previous carry. Out. So what do I have? I have A1 plus B1 plus C0. Again, I get a sum. We call that sum S1. And I may generate a carry out. What happens to the carry out? I'm going to add the carry out. Let me call that C1 because it's generated at this bit position. I'm adding the carry out to the next bit position. Right? Along with, so basically I'm doing C1 plus A2 plus B2 to get some sum. Let me call it as 2. Generating some carry out. Let me call it C2, which is being added to the subsequent bit position. And I basically continue the same process. I get some S3 here, I generate a carry out C3 and so on. At this bit position, some intermediate bit position, basically what I'm doing is exactly the same operation. At every single bit position, I'm doing the exact same operation. Right? I'm taking Ci minus 1, that's the carry out from the Ci minus 1th position. I'm adding that to the ith position. I have Bi plus Bi plus Ci minus 1. I get some Si and some carry out that gets propagated. And then here, of course, again, I will do Cn minus 3, add it together with An minus 2 and Bn minus 2, gives me Sn minus 2, generate a carry out, Cn minus 2. Then I add these two bits along with the previous carry to get Sn minus 1 and I carry out Cn minus. So if I examine the general procedure to add, and if I look at some intermediate bit position, for example, here, what you notice is that every single bit position, I'm doing the exact same operation. I'm adding those two bits along with the previous carry. What that means is, if I'm able to actually design a circuit that can perform this operation, okay, and all I have to do is just copy and paste that modules and make the right interconnections so that I can actually get this operation done. Are you with me until this point? Does it make sense, the approach that we're going to take? Any questions on that at this time? Okay, let me pause. So my idea is, you want to develop this circuit first, and then copy and paste it. That's the beauty about digital systems. Most of the time, you design a module and just copy and paste it. Literally copy and paste it in the actual design process. Of course, to each subsequent module, you're not applying the same inputs. The inputs change, but the operation of the module itself does not change. It's basically fine. Okay, so let's do that. So I'm going to design this module. All right, so let's forget about this. So what this module does at the intermediate bit position is adding these two bits together along with the previous carry, give me a sum, Si, and a carry out. Let me call that Ci. So I want to design that. Let me put that down in the form of a block diagram, a level 0 diagram. How many inputs do I have? I have 3 inputs, Ai, bi and ci minus 1. Bi, bi, and ci minus 1. How many outputs do I have? I have 2 outputs, bi and plus 1. And whatever module that we are designing right now is called the full array, single bit full array. Remember that in the first example, when we designed an adder circuit that can add 2 bits together, single bits together, we call that the half array. We called it the full array. The reason is because this particular module also considers the previous carry. Okay, that's why it's called a full array. In the previous module, in the previous the circuit that we examined, that did not consider the previous carry. Of course, that's not, we did not intend to make that into a module, but in this case, of course, we are actually making that into a module. So this is a 1-bit full array, that's the naming convention. And now let's set out to design this. Again, I'll put down the information in terms of the truth table first, and then I'll start. So I have as inputs, I have ci minus 1, ci, and ci. These are my inputs. As my outputs, I have ci and si as my outputs. Now let's look at all different possible combinations between the input. I have 8 different combinations, starting with 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1. And corresponding sum and carry out. Of course, I'm adding 0 plus 0 plus 0. Sum is 0, carry out is 0 plus 0 plus 1, sum is 1, carry out is 0. 0 plus 1 plus 0, then sum is 1, carry out is 0. 0 plus 1 plus 1, carry out is 1, sum is 0. Because 1 plus 1 is 1, 0, plus 0. 1 plus 0 plus 0, then sum is 1, carry out is 0. 1 plus 0 plus 1, then the carry out is 1, sum is 0. Again, same thing here, 1 plus 1 plus 0 is 1 plus 1 plus 0 is 2. 1 plus 1 plus 1 is 3, which is 1. So that's the truth table. And now I would like to design the circuit that can actually perform that operation. I need to basically implement what is Ci and Si. Let's start with Si first. Okay, then the truth table will be between Ci minus 1, Ai and Bi. And so just different variations and put down information. So I have 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0. And so what are my prime implicants? We have seen this kind of a K-map before, right, in the previous class. In this case, I cannot combine, I don't have any adjacent cells I can combine, so each of my cell itself is a prime implicant. These are my prime implicants. And what is my psi then? Again, I'm not going to do the entire simplification here. We know how we did it in the last class when we had a truth table like this. We had a K-map like that. Right? So my Si in this case would be Ai. There's basically a bunch of exclusive all input variables. Ai exclusive all Bi, exclusive all Ci minus 1. So that's my SI. That's my sum. All right. And let's do a similar thing for Ci. Do that here. Another K-map. Ci minus Ci. Ci minus 1. Ai, Bi. And 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 1. Ci complete 0, 1, 1. And then for Ci, I have 0, 0, 0, 1, 0, 1, 1, 1, 0, 0, 0, 1, 0, 1, 1. Okay. All right. So what is my Ci minus 1? So I don't need this truth table anymore. So one way, of course, here I have adjacent cells, so I can combine adjacent cells. Choose one of them. That's another one. So what is my Ci? Ci would be Ai Bi. Here. Or here I have Ci minus 1 times Bi plus Ci minus 1 times Ai. Right. Now, again, this is a design consideration. Of course, this is the simplest circuit I can implement using the fundamental gates. Right? But Ci, because I've chosen the right time implement, that would be the simplest circuit, no doubt about that. Now, our goal here is to minimize redundancy as much as possible. Okay? Now, the reason why I'm saying that is because, especially when you have these systems where you have for the same set of inputs, I have multiple outputs. Okay? If I can actually reuse some of the output terms, some of the terms from a different output in a different output. For example, if I can reuse some of these operations to obtain, for example, a different output here, then I'm actually, I don't have to, my redundancy in the circuit design is reduced. No doubt that if I were to design a circuit with a single output, that would be the simplest circuit that I can design, okay, using fundamental. However, because I have two outputs here, Si and Ci, if I can express Ci with some terms that are expressed in Si, then I don't have to basically re-implement some of the additional terms of Ci. All right. So how do I do this? So just to give you an example, what I will do is, instead of doing this selection, let me do this and see if that makes sense. Again, in this case, this may not be the simplest circuit with the gate level, but if I implement it this way, what do I get? So here I have implement it this way. If I choose my prime implicants this way, what I'm getting is Ci minus 1 would be Ci minus 1 times Ai prime Bi plus Ci minus 1 times Ai Bi prime. So I can combine them this way. I can take Ci minus 1 as the common factor. And this will say this as Ai Bi prime plus, of course, I have Ai Bi. What is this? What I'm getting is Ci minus 1 times Ai exclusive of Bi plus Bi. So why did I do this? Again, these are not my prime implicants here, right? Because like obviously these two cells are adjacent. I did not combine them. But by doing this, I'm able to get my expression in terms of Ai exclusive of Bi prime, Ai exclusive of Bi, which I'm implementing it anyways for my SI. So I can actually reuse that output term for my other output, CI. So that's the idea. It's not the simplest, but it's the more practical way of doing it. Alright, so now let's actually implement that module, actually showing the circuit. We don't need this anymore. I hope that makes sense. I hope that's clear, these things. When you're actually working with multiple outputs, see if you can actually reuse some of these terms that you implement for an output for a different output, so that you are minimizing the amount of circuitry in your design, additional terms in your design. All right. So, and of course, my SI was implemented as Ai exclusive or Bi exclusive or Ci. All right. So, what is my SI? SI was Ai exclusive of Bi exclusive of Ci. And that's my SI. And my Ci is Ci minus 1 and Ai exclusive of Bi, which I'm able to get directly from here. I don't have to compute that again. As an AND gate, that's Ci minus 1 and Ai exclusive of Bi there plus Ai here. All this here plus Ai. That is my so that's what you have inside the module that we started out. All right. So now I'm able to do this. So I have come up with a circuit that can perform that intermediate addition operation. Ai, Bi, Bi minus 1 inputs. And that's what is inside that full array module. I can take 2 bits, add them along with the previous carry to give me the next carry out and so on. All right. Now, where do we go next with this? As I mentioned before, I can basically copy and paste. Right? Let me do that. If I want to build a circuit that can perform n-bit addition, so that's the module I would build first. This module is built. That's this full adder, a single bit full adder module. Okay? So that's built now. Now, once I know what's inside the module, I don't have to really express that in the same way. I can basically express that with simple block diagrams. In this case, Let me do that. That is done. So we have that down. So now I want to build an n-bit adder. So I will use that module. It takes in at every bit position those corresponding bits along with the previous carry. Let me call that AI. That is Ci minus 1. Those are the three inputs to my system, to that module. My outputs were Si is one of the outputs, and Ci minus 1 was the other, Ci is the other output, right? For the module that I've designed, I take in AI and Bi as the input, Ci minus 1 as another input, and the outputs are Si and Ci. Now I've copied and pasted that module over and over again, n times, for example, because I'm using that exact same operation at every bit position, and I'm dealing with an n-bit adder. That means I have to have n of those modules together. That's another module. I'm using that to add B1 and B1 together. Again, that's my Ci minus 1, Bi, Si, that's my AI input, that's my Bi. Here I'm getting S0, of course here I'm getting A0. Here I'm getting S1 at the sum because I'm adding A1 and B1 together, and then I get C1, and so on, and that's my input module. Again, same module, the same inputs, AI, same configuration of the input, AI, Bi, Ci minus 1, Si, Ci, these are the inputs, these are my outputs. For the nth module, I'm applying An minus 1, Bn minus 1 as the inputs. My sum is going to be Sn minus 1, and I need to make the interconnections now. Alright, so how do I make the interconnections now? I place those modules, I have n of those modules, I have n of those modules, and then I have to connect them somehow so that I can get the right sum, the right carry out. Any suggestions on how to do that? What am I trying to do here? I'm trying to do this addition operation, right? A2, A1, let's say B3, B2, B1, A1 plus B1. Of course, in this case, only in the first bit, I don't have to consider the previous carry. So I can consider that as 0, right? The previous carry is 0. A1 plus B1 gives me S1. And then I have a carry out from this being added to the next bit position, C1. C1 plus A2 plus B2 gives me S2, C2. So at every bit position, I'm considering the previous carry out, adding the carry out along with the 2 bits to get my sum. Right? So how do I do this? How do I connect it? So I get the right sum and the right carry out. In this case, that's my sum, that's the carry out, and this carry out is being added to the next bit position. So basically I'm adding C0 along with A1 and B1. Right? All I have to do here is connect C0 to the input of the next carry in, the next module, the input of the next module, the carry in input of the next module. Likewise, for every stage, I'm connecting the output carry to the input carry of the next module. So basically here, what I'm doing here is I'm doing the n minus 1 module. This will be SCn minus 2. Carry out of this n minus 1 module is being connected to the carry in of the nth module, and that's my sum, and that's my final carry out, Cn minus 1. So now, using this modular approach, I'm able to build an n-bit carry out, an n-bit adder circuit seamless with this modular approach. I don't have to really go with the K-maps now to design from the scratch an n-bit adder. So now I'm working with modules, discrete modules, and putting them together as cascade of those modules, making the right interconnections, and getting the sum out. That's your n-bit adder. So n-bit adder. Again, we have used the modular approach to obtain this. Any questions here? Because that's an important concept. We'll be building up on this concept moving forward. Right, any questions, guys? It's all good so far? Okay, very good. Okay, so let's let me actually just to start simply. Let's actually design a 4-bit adder. Again, it's the same thing, right? I need for a 4-bit adder, I need 4 modules of this. Same thing, copied 4 times. So this is a 4-bit adder. 1, 2, 4. And now I know how to extend it simply. All I have to do is just copy and paste multiple of those to get whatever adder size you need. VI input, VI minus 1, I, VI, AI, VI minus 1, VI, I. In this case, that will be S2, that will be S1. That's going to be A2 and B2 being applied here. It's going to be A3 and B3 being applied here, and that's my CR, the final CR. All right, so that's good. Now, the next step I want to do is, and this actually illustrates the power of the proof complement subtraction method. So let's say I want to modify this circuit. Basically, this can add this particular circuit can add 2 4-bit numbers together, right? 2 4-bit numbers. A3, A2, A1, A0 is my first number. B3, B2, B1, B0 is my second number. So you can basically add those 2 numbers together. Give me a sum. I'm sorry, this will be S3. S3, S2, S1, S0, along with the carry out. Now, if I want to convert that, I want to modify that so that I can make a subtractor circuit, what should I do? Can you suggest a way to modify that to perform subtraction operation? Let's say I want to do A minus B operation. A minus B, which corresponds to A3, A2, A1, A0 minus B3, B2, B1, B0. So I want to do this operation. What modification should I do in the circuit so that that will enable me to do this operation? Any suggestions on that? Complement B. Okay, very good. That's the first step. What happens when I complement B? It's like so for a given binary number, if I take the complement, it's equivalent to saying I'm taking the ones complement of the number, right? When I complement B, I get the ones complement. Oh, by the way, very important. For an adder, recall, what should I do with Ci minus 1 here? This is an adder circuit that can add 2 4-bit numbers together. I don't have to consider, because this is my first bit, I don't have a carry in, so I need to ground, right? Because I don't have a carry in for that. But the subsequent bits, of course, I do have a carry in that I have to consider to add along with the bits. But in this case, I don't have that tag. That's why I ground. Now, if I take the complement of B, I get the ones complement. How do I do the subtraction operation? I take A, if I want to do A minus B operation, I take A, add to that the 2's complement of B, because that's how you negate a number, right? If I have a number B, if I want to negate that, I take the 2's complement of that number. So how do I get the 2's complement from 1's complement? Because complementing B would give me the 1's complement, but I need the 2's complement. Right? You need to add 1. Yeah, I need to add 1. How do I do this? All I have to do is, because I have this, if I just add instead of 0 here, I add 1 here and complement these and these. So now I inverted the B's, adding 1 to that, I get the 2's complement of B, and of course each of these module adds my B to A, and I get the equivalent operation of A, that's 2's complement of B. So now I have the subtractor. All I did was complement B's, add 1 to this C in, the first module, and then I get that. Right? Because the A is 2's complement of B, which is equivalent to say A minus B. So now I have developed, constructed a subtractor circuit directly from the arrow. Okay. So that's very good. But still, the problem is I still need a separate subtractor circuit, a separate arrow circuit here. I want to do those operations, A plus B operation. I will not, once I do this modification here, I will not be able to use this for addition operation. That's a subtraction. If I don't do this complement operation, this is going to do the addition operation. Right? But what if I want to do both, depending on the circumstance? Okay? What I mean to say is, I want to generate a circuit, the same circuit that can perform both addition operation and subtraction operation, depending on how I tell the circuit to do, depending on what I tell the circuit to do. So let's actually do that. Let's actually design a circuit that's called the adder / subtractor circuit. This is a purely subtractor circuit. What I want to design is an adder / subtractor circuit that can do both, depending on how you program it, what you tell the circuit to do at a given point of time. Okay. So how do I design this? Now, this corresponds to, for example, when you're writing the program, right? You write a code, add, then at the hardware level, something should happen. Something should tell the hardware that the programmer expressed the desire to add. So something should happen at the hardware level. Okay? For everything that you do at the program level, correspondingly, something should be happening at the hardware level. You should always have that connection now. Want to design a circuit that can do both addition and subtraction. I need to configure that so basically I need to have an additional input to that circuit. Let me call it the control input. That specifies, so depending on what I apply on the control input. Let's say if I want to add, I apply let's say a 0 on the control input. That implies that the circuit should be configured as an adder and should basically give you A plus B operation. On the other hand, if I apply a 1 on my control input, that implies I should basically configure the circuit at the hardware level to be a subtractor, and I basically should get A minus B operation. Yeah. So if I'm trying to configure a same circuit to do multiple things, then I need to have a control input. So that's a design principle that you should think about, you should make a note of. And you should always have a control input. And then we place a value on the control input that would reconfigure that circuit into what you want that circuit to be. just like here, if I place a value of 0 on the control input, I should do an A plus B operation. 1 on the control input should do A minus B operation. So that kind of corresponds to your program. When you write A plus B in your program, at the hardware level, what is happening is you're applying a 0 on the control input, and vice versa. So if I'm on the program, I'm writing A minus B, do A minus B. That means at the hardware level, you're applying a control input of 1 on the control, and then that basically modifies or reconfigures the circuit to do that operation. Oh, that makes sense. Okay, now how do I design this? How do I design this? How do I introduce this control input here so that when I apply 0 here, I can say I do A plus B, the 1 on this input, I do A minus B. Okay, so that's not very intuitive, so let me actually explain that. So this is very important. I'm working with control inputs now. Okay. Now, so when I do a control of 0, what should happen is my A should go as is, my B should go as is. Okay. My A should not be inverted, my B should not be inverted. When I apply a 1 on my control input, my A should go as is without being inverted. However, I need to somehow invert B depending on the control input. So how do I get that operation? So let's examine this simple, again going back to your XOR operation. Let's see what an XOR gate does. So let's say you have an XOR gate. As one input, I say I would place B. Okay, let me say BI. Okay, and as the other input, I would apply control. And let's see what happens here. What happens to the output F? Again, going back to the truth table, let's draw the truth table for the XOR gate. In this case, my inputs are BI and control, right? I have two inputs to this XOR gate. What are my outputs? Okay, these are the different combinations between inputs. That's my output F of the XOR gate. Again, that's basically an XOR gate. So 0, 0 is 0, 0, 1 will be a 1, 1, 0 would be a 1, and 1, 1 would be a 0. That's an XOR gate, the truth table of an XOR gate. Okay. All right, but if you look at this from the perspective of the control, what is happening? From the perspective of the control, if my control is 0, which happens in these two instances, what is happening to the output in terms of BI? So you examine it in terms of BI and F. From the perspective of the control, examining BI and F, what is happening to the output? When my control is 0, my output is the same as the input, BI. You see here, when my control is 0, my output follows the input. My output here is, my BI is 1, my F is 1. My BI here is 0, my F here is 0. So the output follows BI. If the control is 0, as long as the control is 0, the output follows the BI. What happens when the control is 1? It happens in these two circumstances. Again, from the perspective of control, if I place a 1 on my control, what is happening to the output with respect to BI? The control is 1, my output is the inverted version of BI. You see this? My BI is 0, output is 1. BI is 1, output is 0. So by using the XOR gate and applying the control on the XOR gate, I can either invert my BI, I can get an F which is the inverted version of BI, or get an F which is the non-inverted version of BI, or BI itself. So I can control by will using the XOR gate. So what that means is, instead of using a NOT gate, why not use an XOR gate? on my B inputs. So each of my B input would feature an XOR gate, B input XOR gate. What is the other input going to be? The other input is going to be the control, right? Because we want to use the control to either send B's and modify B's as is, or the inverted version of B's. So the other input for each of my B input, for each of these XOR gates, yeah, that's going to be my control. For each of my B's, that's going to be B and the control. So for each of these XOR gates, one of the input is the control, common input, and the other input is going to be the B0, B1, B2, B3. Okay, Alex, do you have anything to say? You raise your hand. Yeah. That's a good question. What should I do with this? What should I do with this? I have not done anything with this yet. So you can see when I apply control of 0 here, what happens to B's? Control of 0, my B's goes through the XOR gate unmodified, right? Nothing, it doesn't change the value of B's when I apply control of 0. According to this, when I apply control of 0, B's goes out as B's. The output follows the input. So if you can think of that as, if I want to add them, you can think of that as being configured as an adder circuit, right? And the control is 0 because I'm adding A to B, unmodified version of B. I'm basically doing an addition operation. But what happens when I apply control of 1? When I apply control of 1, of course this has to be grounded when I'm adding it, or at 0 when I'm adding it. When I apply control of 1, what's happening to B's now? Apply control of 1, my B's are being complemented, right? When I apply control of 1, my output follows, my output is the complemented version of B. As you can see here, B is 0, F is 1, B is 1, F is 0, right? So when I apply control of 1, my B's are all inverted. So I'm basically adding A to the inverted version of B, but basically an inverted version of B is taking the 1's complement of B. I need the 2's complement. So what should I, how do I configure my C in here? What should I do so that it works both ways? When I'm doing the addition operation, it's adding the correct C in. When I'm doing subtraction operation, it's doing the correct C in. What should be applied at C in so that it works both ways? Yes, connect the control to the first carry. Absolutely right. And that makes your circuit perform both operations. You can configure this circuit depending on what you apply on the control. Now you can configure this circuit as an adder or a subtractor. So that's why we call that the adder / subtractor circuit. Okay. Any questions on this? So again, the design principle is every time you want to design a circuit, a single piece of hardware that can perform multiple operations, multiple functions, then you have to come up with a control input. If I want to perform, let's say if I design a circuit, that can perform 4 different operations, the same piece of hardware, but I want to reconfigure them so that it can perform 4 different functions. How many control inputs should I have? I'm trying to design a circuit or a piece of hardware that can perform 4 different operations. I need 2 inputs, right? 2 control inputs. So 0, 0 would be one operation, 0, 1 would be one operation, 1, 0 would be set to another operation, 1, 1 should be set to another operation. In this case, I have two operations. The same piece of hardware. In this case, I've designed this hardware. I want to configure that as an adder or a subtractor. I have two different cases here. So I have a single input control, single bit control. Right? All right. So again, so moving forward, it's very important that whatever you're doing, whatever you're trying to design, you need to relate that to what is happening, how a programmer would actually write a program, and correspondingly what changes are happening are happening at the hardware level. So you need to always make a connection, even again, at least at the intuitive level. It's always important that you actually make the connection, so that you can actually see now things, because now we are actually getting into the hardware part. You'll see it actually makes it more interesting. Now you'll appreciate, the program, how the programs and the hardwares are both linked at the high level. All right. Now, with that, at least our discussion on the full adder / subtractor is done. But let me actually ask you this question. Do you see any potential issues with this circuit? Let's say I'm trying to design a 32-bit adder circuit. Do you see any potential issues there? Or let's say I've designed a 4-bit adder, and I've become very ambitious now, and I want to basically design and because now it's as easy as simply cascading multiple units, right? So basically, if I design a 4-bit adder, all I have to do is just copy and paste it. So let's say, if I have two 4-bit adders, I can simply cascade them together to make it into an 8-bit adder, right? In fact, you can actually buy them. You can actually buy 4-bit adders, and then you can actually make an 8-bit adder, and by cascading them together. Now, if I become too ambitious, and let's say I want to design, let's say, a 64-bit adder, and I just keep adding on modules to it, just keep adding on modules. What will be a potential problem you think will maybe happening? You can speak up. It's more quicker that way. Yeah. It won't be efficient. Can you elaborate on that? What makes it inefficient? Efficiency in terms of what? Is it poverty? In terms of power consumption? What's that? And what? I'm sorry? Too big? Well, okay. So I guess that's something that we can work with. I mean, because now everything is so small, I can basically implement that as an integrated circuit on the same chip, and that should be fine. I should be able to get around that problem. But a bigger problem is there, right? If you notice the circuit, when I'm trying to get the answer, let's say I put my inputs here, and I'm looking for my answer. I'm monitoring these outputs, my S0 through S3. I'm trying to monitor them. Now, as soon as I put these inputs, do you expect the answer to be the right answer? Whatever you get as the output, do you think the output is the right answer in the first instance? Does it make sense? As soon as I apply my inputs, I'll get some answer, right? Some values on my answer. And turns out that no, it's not the right answer. Why? Because if you notice this, if I notice at each module what is happening, right? And I'm taking these inputs, I'm computing my sum, I'm computing my carry out. Okay? That means if I want to get the right answer here, first I need to get the right answer here. The right Cin should be applied here. That means this circuit has to wait for this circuit to complete the Cout operation. Right? Now, every circuit is not infinitely fast. Okay? What I mean to say is, every circuit will have its own propagation delay. That means if I have a gate, okay, I apply my inputs to this gate, I get an output F. As soon as I apply my inputs, I'm not going to get an instantaneous switch in the output. There will be some propagation delay, which we call that a switching delay, because my gate has to switch from one value to the other, right? It has to either switch from 1 to 0 or 0 to 1, and there will be some slight delay associated with that. Of course, it's very small for a single gate, but if you have multiple gates cascaded, the delay can get added up. For example, here, that's exactly happening here, right? Here, my Ci, if you recall, it has to perform this operation, Ai times Bi plus Ci minus 1, Ai exclusive of Bi. So each of these gates has to basically operate, switch the value to get my Ci. Now, to get the right sum here, S3, I need to get the right C, in this case C2 being applied on this particular circuit, in this particular module, right? So for my right C2 be coming here, I need to get the right C1 here. For my right C1 here, I need to get the right C0 here. So as you can see here, my propagation delay gets extended, right? From going from this module to this module, I'm waiting for C out to be calculated, C1 to be calculated, C2 to be calculated. So my propagation delay gets added up. And if I add too many modules, that's going to be just getting added up, and it will be a delay that you can actually sense. For small modules, not so much of a problem, because the propagation delay is not much. But if I extend it to a very large module, like 64-bit or maybe more than that, 128-bit, then these propagation delays can get added up, and whatever answer that you're getting here, you need to wait. Of course, it will work, but you just have to wait longer time for the answers, for the sums to settle down, giving you a final correct sum. Okay. So if my propagation delay is T for a single module, if I have n modules, the total propagation delay would be T times Tp. Let me Tp propagation delay. N modules will be n times Tp. And again, you should be able to notice that for very large modules. Does it make sense? So again, something that you need to be cognizant about. You cannot just indefinitely add modules to it and then expect that you get the correct sum right away. You will have some delays there. It has to go through a sequence of transitions until it settles down on the right side. Okay, so with that, that's the first example of modular design. Okay, and in the next class we'll take this up a little bit. We'll increase the notch a little bit higher. We'll look at the BCD adder in the next class. We'll try to come up with a modular design approach to build the BCD adder circuit. Okay. All right. With that, let me end this class. If you have any questions. Okay, you have everything you need to finish the homework. I would think so, yes. It should be, although for the final problem, you know what, let me just extend the homework, because you should, with whatever we have covered so far, you should be able to do the problems, but for the final question, I would like to do it in a more elegant way. Okay, and you'll get some more idea about the final problem once we covered the BCD discussion in the next class. So I will extend it until Tuesday for the submission, so you'll have time to work on the final. Yes, I'll be adding the today's section in Blackboard, absolutely. Yeah. All right, so anything else? I'm just going to stop the recording now.